Yeah, I see people start to join in, so I think it's good time for me to start and introduce the speaker. So this is our last day of the talk, last talk of the day, and also the last talk of this workshop. And our speaker is Professor Weina Wang from CMU. She's a rising star in the area. Weina is assistant professor in the computer science department at Carnegie Mellon University. And her research lies in the broad area of applied probability and stochastic systems, with applications in cloud computing, data centers, and privacy-preserving data analytics. She did her postdoc at the University of Illinois at Urbana-Champaign, jointly with Arizona State University from 2016 to 2018. She received her PhD degree from Arizona State University in 2016, and her bachelor degree from Tsinghua in 2009. Her dissertation has received the Dean's Dissertation Award in the Aaron Fulton School of Engineering at Arizona State University. And also she received the Kenneth Savsik Outstanding Student Paper Award at Sigmatrix in 2016. Okay, and today she's gonna tell us how to quickly detect misinformation using a Markov optimal stopping approach. With that, Weina, please take it away.
Thank you, Lei. Let me start sharing. Yeah, thank you for the introduction, Lei. And I'd like also to thank all the organizers for organizing this wonderful workshop. I'm Weina from CMU, and I'm very glad to be part of the workshop. And I'd like to talk to you today about our work on misinformation detection. So misinformation has been a problem of increasing concern. So as talked in the first talk today, it does a lot of damage to the society. So especially right now during this pandemic, so misinformation actually costs people's lives and health, and potentially leads to assaults and racism. So as WHO previously said, so this infodemic, which refers to the misinformation surrounding the COVID-19, just spreads as fast as the virus itself. So there's a very pressing need for the media, especially the social media, to take countermeasures to battle misinformation. And also, like, since infodemic shares some similarities with the pandemic, so I hope some of the modeling and analysis techniques we developed in our work can provide some inspiration for research on that pandemic. Okay, so this is a joint work with Hong Hao from Michigan, Xiaohan from UIUC, Lei from Michigan, and so to get a handle on misinformation, let's start with a very short message here. Okay, so this is a very simple message. It says drinking bleach cures coronavirus. Okay, so what do you think? Is this misinformation or real news? If you like, you can indicate your thought using the yes/no button in Zoom. Yes means this is real news. No means this is misinformation. So, okay. So I think yes means okay. So we have a 1 versus 1. I've already indicated in my choice. I believe most people would agree this is actually misinformation. So actually, so if you think this is misinformation, then what is it in this message that makes people think this is misinformation? Okay, so yeah, this one is kind of clear because it just goes so against of our common sense, right? So drinking bleach here never sounds like a good idea in real life, and the cure is a pretty strong word to use. And typically, it's really rare to find a cure for disease, not to say within such a short period of time. Okay, so most likely this is a misinformation. But what about this one? Okay, so this message says new evidence from a large study of 1,063 patients showed that chlorine dioxide treatment lowered the death rate by 80% among hospitalized COVID-19 patients. Okay, so what about this one? Is this misinformation or real news? Okay, so without further examination, I would say it sounds plausible, right? So I would give it the benefit of doubt, like because yeah, I just couldn't tell from the wording of this message. So what if what if you are running a social media platform and you see such a message circling around? What are you going to do to judge whether this is misinformation or not? Okay. So a natural approach is to do fact checking. So for example, here, what is this study? Where is it published? If it's published in a reputable journal, then maybe you want to read the article to see if the article is really saying this, because many times it could be misinterpreted. Okay, so indeed, the fact checking has been adopted by many major social media platforms. And for example, Twitter has this fact checking label on some of the tweets, which directs you to a curated page of more information. Okay, and so usually fact checking is done by human, actually by professionals who are trained to do fact checking. So typically it's very accurate, but it takes time. Like for example, for this example, if we want to track down this paper and read the paper and understand it, it takes a significant amount of time. Okay, so CNN once counted more than 20 false or misleading claims from Trump just within one speech. So if this is the only place you need to check, then probably fact checking could be a viable option. But if you're running a platform like Twitter, which has over hundreds of millions of tweets every day, then doing fact checking can hardly cover an even fair fraction of all the messages generated every day. Okay. Okay, so another approach that has been tried is crowdsourcing. But as you can imagine, so basically this approach is to let the readers report what they think is misinformation. So similar to many of the crowdsourcing approaches, you can imagine that the reports could be noisy and unreliable, and it's hard to process. Okay, and another natural question is, can machine learning solve this? So we know that machine learning has solved a lot of problems and has made its way to basically most of the research areas. So can machine learning come to rescue for this misinformation detection problem? So indeed, there has been a lot of research which uses machine learning for misinformation detection. And a traditional approach is to focus on the language features of the message and use techniques from natural language processing. So, but if you look at this example here, language-wise, it looks very similar to some real news. So actually, this is indeed misinformation because I cooked it up. So I took this sentence from a real news and I just replaced the treatment name and the disease name and changed the numbers slightly. Okay, so so I would say the language doesn't give it away for this example. So some more recent work incorporates user features into the classification. And those algorithms can be very accurate if given enough information. So here, enough information means you collect a trace of data, and then you have a lot of user information on the same message, and then you make use of that to do the classification. Okay, so but what it doesn't tell us is how much information is actually enough. So it doesn't give a principled way of choosing of deciding how much information is enough. So this actually brings up a very important shortcoming of the existing approaches, which is the detection time is not taken into account explicitly. So the algorithms here are more like an afterthought. So after a message has been retweeted for a while, then you look at the data trace and see if this is misinformation or not. Okay, so yeah, so basically, if we want the detection to be quick, then we need to take into account of the detection time. Okay, so then we have now we have seen the pros and cons of the current some of the current practices. Now we are ready to articulate what we actually want to achieve in misinformation detection. So we definitely, clearly, we strive for accuracy, and given the volume of information nowadays on online platforms, we want the approach to be really scalable, to cover like a fair amount of information being generated every day. But more importantly, we also want the detection to be quick. Okay, so we want to, if this is misinformation, then we want to contain the spread as soon as possible to limit the damage it does to the society. Okay, so if you think of this scalability here as a high throughput for the detection mechanism, then the detection time here can be thought of as the delay. Like if we want a quick detection, then that corresponds to a very low latency of the mechanism. Okay. So even if we have the capacity to process a large amount of information every day, if all the messages you process are from a year ago, then it wouldn't be so useful. Okay, so yeah, so this I guess I have more stops than recommended. But like I just give myself a reminder here. So is there any questions so far?
Yeah, there is a question in the chat. Harsh, do you want to just go ahead and ask away now? Okay, maybe I can repeat the question. So the question is about what kind of user features are being used there.
Okay, yeah, so what we use, I believe, include, for example, the how long the users have registered and how many followers and followees the users have, and yeah, some kind of like a profile information. So yeah, does that answer your question, Harsh? Yeah. Okay, good. Yeah, okay, so just a quick pause here. So okay, so now our goal is to achieve all those three at the same time, and a start point of our approach is the following. Okay, so you would feel very differently if this message is coming from a PhD in epidemiology, and when it's coming from someone who just tweeted potato cure cancers like a week ago, right? So the track record of the user who retweets the message gives like has some implication on the credibility of the message. So then because the message itself is really complicated to read, what we did is we want to focus on the profiles of the users who spread the message. So we look at those users instead. Okay, so does this idea actually work? So on real data. So we tested it on data set, and let me show you some of the evidence here. Okay, so we have a data set from Sina Weibo, which is actually the Chinese version of Twitter. Okay, so then the data set is labeled. We have many messages which are labeled as either real news or misinformation. So we use those labeled data to train a classifier on the users using those features of users asked by Harsh. So this classifier classifies users into two types based on those features. Type 1 represents the users who are more likely to spread misinformation, and the type 0 represents those who are more likely to spread real news. Okay, so we can call the first type 1 users naive users and type 0 users savvy users. Okay, so so by the way, here throughout the talk, when we have a binary representation, I always associate 1 with misinformation because that's the thing we want to detect. Okay. So after we train this classifier, we tested it on test data, and here's the histogram of the scores for those users who actually spread misinformation. So based on our classifier, higher scores correspond to type 1 and the lower scores correspond to type 0. Okay, and then you can see here more users from type 1 spread misinformation. Okay, and here's another histogram for the users who spread real news, and then you can see more users of type 0 actually spread real news. Okay, so those two figures demonstrate a strong correlation between the user type and the type of the message, which supports our use of user type as an indicator for the message type. Okay. So actually in our approach, we actually took this a little bit further. So when we observe a message being retweeted, actually 2 people are involved. It tells us who is retweeting from whom. So for each hop of the information spread, we have 2 users and a link between those, edge between those 2 users. So we look at the type of those edges. So conceptually, the type of an edge is determined by the types of the users on the 2 vertices. Okay. So for example, here, if Alice is of type 1 and Bob is of type 0, Charlie is of type 1, Dave is of type 1, then we have all those edge types. So here 1, 0, 1, 1, and 0, 1. Okay. Okay, so now we have a sequence of those edge types. We denote them using Z with the index indicating the order of the message. So basically, this index is determined by the time when the retweet happens. Okay, so this sequence of edge types are our observations of the spreading process of a message. So now we have those edge types, and then in our spreading model, we model this edge type sequence as a Markov chain. And the transition probabilities of this Markov chain is determined by the message that's being retweeted. So if this message is indeed a misinformation, then we have a set of transition probabilities as shown in the left table here. You don't need to read into those numbers. We estimated those numbers from the data set. Okay, but if this message is a real news, we have a different set of transition probabilities. So you can see the difference between those 2 tables. Okay, so under different message types, the dynamics of the Markov chain is different. So this is, of course, a very coarse model because we are only modeling the 1-step dependence using a Markov chain. So you can, there could be a lot of work to do to explore more complicated spreading models. So for example, the next edge type could depend on all the past edge types, and as well as the structure, the network structure that represents the relationship among users. Okay. But one thing we need to consider if we want to use a more complicated model is there's a trade-off here. If you use a more complicated model, then that means you have more parameters to estimate from the data. Okay, okay, so with this spreading model, we're going to formulate the detection problem. So we keep track of this time sequence of type edges, those are our observations or samples. So suppose this one is our current observation. Then whenever a new observation is generated, like which means the message is being retweeted one more time, then we need to decide whether we want to conclude right now whether this is misinformation or not. And if we want to conclude right now, then what is the conclusion we want to declare? Okay. So we can model the conclusion time using a stopping time with respect to this process of edge types. And so here we think of time just as the number of retweets that has happened. Okay. And then like what we, as to the decision on what we want to declare, we want to design a detection rule to tell us what message type to declare. Okay. And recall that when, at the beginning we were saying we wanted to do the misinformation detection quickly, accurately, and scalably, right? So let's focus on the accurate and quick aspect first. So here the key here represents the number of users a message reaches before we conclude. Okay. So if this is misinformation, then that means the misinformation reaches T people. Okay. So then to limit the damage, then we don't want the misinformation to reach too many people. So we build this propagation cost of misinformation into our objective function. That's the first part of the objective function. And then, like obviously, if we make a wrong decision when we determine what message type to declare, then it has some bad impact. So we also have a cost that comes from the detection error. Okay, so we want to minimize the total cost to take into account of both aspects, like speed and accuracy. Okay, so questions so far on the model and the formulation? Okay, if no question, I'm going to continue. Just want to make a quick stop here.
Yeah, go ahead.
Yeah. Okay, so now let me go into the details of this objective function. Okay, so we have those two parts of costs. So for the cost of misinformation propagation, like as we said, T is the number of people the information reaches. So we want to model this as a linear function in terms of T, and this is C sub P here is the cost per user. But this cost only happens if this is indeed a misinformation. Okay, so then we put the indicator function here, which is 1 if the truth is that the message is indeed misinformation, and it's 0 otherwise. Okay. So that's why we call it the cost of misinformation propagation. And for the second part, which is the cost of the detection error, this is modeled at as in a regular detection problem or like a hypothesis testing problem. So basically, we can make two types of errors. Either we claim this is misinformation, but the truth is that it's real news, or the other way around. And for different types of errors, we can have different costs. Okay. So with those notation, we can rewrite the objective function in this form. Again, like we want to choose our stopping time T and the detection rule to minimize the total cost. Okay. So let's focus on this second part first. This is the cost for detection error. So I put a reminder on the right upper corner just to remind ourselves of what the notation means. Okay, so let's look at this part. So this part is actually very easy because once we stop at a particular time, it just becomes the regular minimum cost hypothesis testing problem. Okay. So, but let's still write down the solution because it's related to also the solution for the first part. Okay, so for this problem, in the solution, we need to keep track of the posterior probability for misinformation. So recall that Z1 through ZK are the edge types we observe up to the kth time K, okay? So then the optimal detection rule or decision rule is a thresholding policy based on pi sub k. So to illustrate this using a picture, so this in this picture, the x-axis is the posterior probability, and those two lines represents the two types of the cost for the two types of errors. So to minimize, at any for any value of pi, when we make a decision, we need to incur one of those two types of costs. So to minimize the overall cost, we want to make sure we are on those lines that have a smaller value, which is represented by the red line here, the red curve here. Okay. So under this optimal decision rule, the minimum cost can be written in this form. Okay. So if we view this red curve here as a function g of pi, then this can be written as g of pi sub k, which is the current posterior probability. Okay. Okay, so yeah, half of the problem is solved, and let's go back to our original formulation. With this optimal detection rule, we can rewrite the detection error in this form. Okay, so now let's look at the first part, which is the propagation cost, and the propagation cost here. So this in this part, this indicator function here is causing some problems for us. So it is not some quantity that is observable, right? Otherwise, we won't need to do all of those, right? So it's not observable. And yeah, so to deal with that, we actually show that this expectation here, the whole expectation for the first term, we can actually rewrite it as just this expectation here, where we replace the indicator function by the posterior probability. Okay, so this is true because t is a stopping time, and that allows us to make this substitution. Okay, and now it becomes it's good because this posterior probability is something we actually want to keep track of. We can observe it. So this first cost here, first part of the cost here becomes something that's observable. Okay. So then that means our problem becomes a Markov optimal stopping problem. If we write the Markov chain, represent the Markov chain in this way, where the state consists of the posterior probability, the edge type z sub k, and the current time index. Okay. So okay, so this can be formulated as a Markov optimal stopping problem. And sorry, maybe I'll go back a little bit. Sorry.
Hey, Wina, if you don't mind, there's a question in the chat.
Sure.
Aranya, do you want to unmute yourself and ask a question? Oh, okay. So he wants me to read out. So it's kind of long. Just curious, since you mentioned that the transition matrix will be different for real versus fake messages, can we use spectrum information like eigenvalues, eigenvectors of the transition matrix to model the detection error? If so, then the second component of the objective function can be modeled using eigeninformation, which may be slightly more trackable as seen in the convex optimization literature.
Okay, I see. So yeah, we haven't really exploited the structure, the eigenstructure of those matrix information, but I think this is a very good question. So what we have explored here is the difference between those two matrices, which could be related to the spectral information from those two matrices. So yeah, so that's something maybe I'll need to think more about.
Yeah, there's another question. Yun Xiu, do you want to just unmute yourself and ask?
Sure. Can you hear me?
Yeah.
Okay, good. So my question is actually regarding how will you decide if a certain piece of information is true or not? Because I think such decision is quite subjective.
Right. Yeah.
Yeah.
Sorry, go ahead.
No.
Yeah, I totally agree. Like it's a very complicated subject, and if you look at the literature on misinformation, there's actually a lot of debate on what counts as misinformation and what doesn't. Right? Sometimes it's opinion based. So here, like I think in the data set, like if they want to label it as misinformation, it actually has to have some factual mistake in the statement. So you can get some like a factual test on it, like it directly contradicts something that's established as a fact.
I see. So in your work, you will use a factual check.
Right. Yeah. So the data set we have is already labeled, and that's when we test the things, we use that as the underlying truth on the tested data.
Got it. Thanks.
Hey, Weina, maybe another clarification question. So the transition matrix you mentioned, we assume it's assumed to given to you, right? In your
we
algorithm.
estimate those in the data set, right?
Okay. I think. Thanks.
Yeah.
So maybe just a follow-up question to Yunshu's question, which is that, of course, there's this underlying question of subjectivity and how to determine what is true or false. But there's, I think, another issue here, which is that often things are not black and white. They're not necessarily true or false, but they're somewhere in between. And elements, some information can have true elements and false elements. And I'm wondering, what's your perspective on that is, and how that would factor into, say, such a...
So that's a very good question. I totally agree. Like sometimes, that's why sometimes you see on the news, this is misleading and exaggerating, or like they use different words for different kinds of messages, right? So I think a more general model is like the message is not just like two types. Like you can have more types for the messages. Like if it's clearly truth, then that's the best type maybe, and if it contradicts with some fact directly, it's the worst type. But you can have something in the middle that kind of quantifies the degree of truth in the message, and then like for different degree, maybe you want to take different kind of countermeasures. So here, like if we are thinking, we didn't like think of any specific countermeasures you want to take, but I would imagine if this is clearly wrong, then you can just directly claim this is totally wrong. But if it's somewhat misleading, then maybe what you want to do is to just provide more perspectives on the same topic. You give references to more of the more articles on the same subject, so like different levels of actions.
Great, thanks. And could that kind of be just incorporated into this optimal stopping framework?
So yeah, I think it definitely becomes more complicated, but I would think like you can still have you may have like it's not the black and white. It's not like you want to stop it or not. Like it could when you. Yeah, I think maybe like one direct way of generalizing this is to use different costs for different types of messages. Here, this is only for misinformation. Maybe you can have different numbers for different type of messages. Yeah, that's like the thing that comes into my mind directly.
Great, thank you.
Okay, so this is an unplanned stop. Actually, I'm going to just show you the solution to our problem. Okay, so typically this kind of Markov optimal stopping problem here, if you have the k in the state, the solution could depend on k, which is the time index. So you have a time dependent policy. And that could be hard to implement sometimes because it's very complicated. You use a different policy for every different time index, right? But interestingly, we find that for our problem, the solution is actually time independent. Okay, so let me show you what the solution looks like. Okay, so this is our solution, which is represented by just 4 pairs of thresholds, and each pair corresponds to an edge type indicated as the superscript here. So then this pair is for the edge type of 1, 1, and each pair consists of a lower threshold and a upper threshold. Okay, and then our stopping rule is like this. So we keep track of the posterior probability and the current edge type. Okay, and as soon as this posterior probability goes out of this range, we just stop. Okay, so let me just use a quick example to illustrate this. Suppose the current time is time 3, and we are observing a edge type of 0, 1. Then we want to go to this pair that corresponds to 0, 1 and check if the posterior probability is within this range or not. If it goes out, we stop. Okay, so you can clearly see that this is a time-independent solution. Okay, so and moreover, this policy is very simple. It's just represented by 8 numbers, and it's quite easy to implement because we just want to check whether something goes out of the range or not, and we need to keep updating those observations. Okay, so yeah, that's the advantage of this stopping policy. And next, I want to explain a little bit why we can get a time-independent optimal stopping rule. Okay, so this next page is going to have basically all the most of the equations of this talk. Okay, so we want to solve this Markov optimal stopping problem. Recall that we want to find stopping time t to minimize the cost function. Okay, and then you can write out the value function. So the value function with the subscript k here means the optimal value, the minimum cost, if we require the stopping time to be larger than or equal to k, right? So if you have to stop after k times loss, then this is the minimum cost that you can get. Okay, so then we can actually do a change of variable. We first separate this cost into 2 parts, here and here. Okay, and then we can actually show that this second part here, the expectation, has a very simple form because the posterior probability process is a martingale. Okay, so because it's a martingale, so when you take the expectation, it just becomes the current observation of the posterior probability. Okay, so this is very good because we can, let's put this back, and this corresponds to that term, and do the change of variable for the first term. Then what we have is this. Okay, so the k, the time index, only appears here. Okay, and now let's see how this would affect the optimal decision. So to decide what is the optimal decision, we can write out the Bellman equation. So the Bellman equation here is like this. So this is the value function, and then it's equal to the minimum of 2 terms. The first term is the cost if you stop right now. Okay, so this is the error cost, and this is the propagation cost. Okay, and the next term is the optimal cost if you have to go at least 1 step further, which is just means you should continue instead of stop right now. Okay, and so if the first term is smaller, then we would stop. So let's see, this part here, let's make use of the factor we just established. Then we can rewrite this as a form, in a form like this. Okay, and observe that the k appears both here and here. Okay, so when you choose which term is smaller, the k doesn't really affect doesn't really affect your decision, right? Because we have CP times K pi on both of the terms. Okay, so then that means our optimal decision rule shouldn't depend on K, which means it's time independent. Okay. Okay, so yeah, any questions so far? Okay, so yeah, so now let's put everything together. I have shown you the optimal stopping rule, and now let me tell you what is the whole algorithm we have here for detecting misinformation. So based on the detection rule actually and our model, so our algorithm, which we call QuickStop, actually has two parts. The first part is like it needs to can be run offline. So basically we run some machine learning algorithm to get the classifier for the edge types. So once you get the edge types, then you estimate the Markov chain parameters for the under different types of messages. And then like based on that, we can compute our thresholds in the optimal stopping rule. Okay, so then after we get those threshold numbers, the online part is very easy. We just keep track of posterior probability, edge type, and we just run according to our stopping rule. We stop at the earliest time that this posterior probability goes out of this range. And also, like if it goes out of the range from the left, then we declare this is real news. Otherwise, we declare, if it goes out of the range from the right, we declare this is misinformation. So actually, you can show that this is consistent with the optimal detection rule, which is established before. Okay. Okay, so this online part is really light, and that's what makes this algorithm scalable. Okay, so let me show you some experiments we did on the data set. So first, this is a demonstration of how the dynamics work, how the dynamics looks for this algorithm. So for in this graph, the x-axis is the number of posts, and the y-axis is the posterior probability we're keeping track of. And we have two curves here. The red curve is a curve that corresponds to a misinformation, and the blue curve corresponds to true news, real news. Okay, so you can see that we kind of, for example, let's look at this blue line, which is the news one, and we keep track of this to see when. Actually, what we couldn't show is actually for each point here, you can get the edge type, and there will be a pair of thresholds that you should be using, and then you compare this with those two thresholds. But we can observe that at the end, when we stop, at this point, the edge type must be 0, which is 0, 0 in our notation, and it goes below this threshold, so that's why we stop. And it goes below, so we declare this is news. Okay, and for misinformation, in general, it should cross some threshold upwards, and this is the threshold it crosses when we stop. Okay, and we can see from, at least from this example, the misinformation one stops earlier than the news one. Okay. And so we can actually adjust the costs of our algorithm in our algorithm to adjust the trade-off between accuracy and speed. So if we change this cost to be higher, so this is the propagation cost. If we change it to a higher value like 0.8, then intuitively we should stop things like earlier on average, because we don't want to risk, we don't want to take the risk of letting misinformation spread. Okay, so then like you can indeed observe in the graph on the right, on the same traces, actually the misinformation indeed stops much earlier, and the news also stops earlier. So the threshold becomes smaller for this particular edge type. So then you cross this, it's easier to cross this threshold. Okay. Okay, so this demonstrates the dynamics. Then let's see how it actually performs on the data set. Okay, so here we compare our algorithm QuickStop with a lot of other algorithms in the literature. So most of them are based on machine learning algorithms. So here, because they don't have like their algorithm just takes whatever trace you give to it. So to compare like the speed of those algorithms and the trade-off between speed and accuracy, we actually give the algorithms some deadlines. So for example, we limit the algorithm to a deadline of 100, which means we just truncate the trace at 100 posts and run the algorithm to see what is the accuracy. Okay, so the x-axis is the deadline and the y-axis is accuracy. And our algorithm, it decides whether it wants to stop by itself, right? You cannot pose a deadline for it. So then the x-axis here represents the average number of posts it takes to stop. Okay, so then you can see from this this figure, we stop like our accuracy is better than most of the other algorithms for the same amount of information, for the same same amount of posts, which means the number of users the message reaches. Okay, and it's like most of the time it's just much smaller than like even if you run some algorithms for many posts, it still cannot achieve accuracy as high as our algorithm. Okay. Okay, so questions?
Maybe I can ask a quick one. So in the, I think the previous slide you mentioned like it stopped early for fake news, but kind of relatively late for the true information. Can you comment on that?
Yeah. So let me see. So intuitively, like because we want to minimize, because we are minimizing the total cost, and if this is indeed a misinformation, then that has a propagation cost. Okay, so then we wanted to stop earlier. For true news, for the amount of time it spreads, it doesn't incur any propagation cost. So you can afford to let it run for a longer time. But like to be more accurately, even when you declare it's true news, it's real news, there's still a small probability it's actually misinformation. So that part like is still counted towards the propagation cost. So that's why like we don't let the news run forever. So
right. Okay.
It still stops. Yeah.
Okay. Yeah. Thanks.
I have a quick question. So this data set that you have, so somebody has already classified it as fake news or real news, right?
Right.
So how did they do it?
Yeah, I'm not exactly sure, but I would imagine people would like want to do it using some fact checking. Okay, so it's probably not. I'm not sure. I need to check with how he runs the experiments. Okay, so I guess the reason I'm asking is that it'll be interesting if the experiment somehow compared. I think Tawhid mentioned, for example, he had some program that he was comparing his algorithm to bot something. So one interesting comparison would be to if there are existing programs that detect whether something is fake news or not, then it might be interesting to compare your algorithm to an existing algorithm to see if you actually are able to detect more fake news or less fake news. And I don't know how he did the comparison. I guess even for that, you need to have some ground truth. But somehow he had some ground truth, but compared it using some algorithm
So that's the tricky part here. Is
yeah, sorry, I didn't quite follow the comparison here. So how is that comparison different from, for example, the comparison we did here? I guess my screen froze.
I guess what I'm saying is, so what is the comparison you're doing here? Maybe I didn't understand the comparison you're doing here.
Can you see which is the screen you're seeing? I feel like
right. Demonstration.
You're on the dynamic. It's not the last slides which show you're comparing with a bunch of other elements.
Yeah, let me just quickly like stop share and start again. Okay. So for those like other algorithms, so some like they also check. So for example, they also look at which users are spreading the same message, and then like it checks all the users on these trees and use the whole thing as your like.
So I guess what I'm asking is that these algorithms are all statistical or network science based algorithms like yours, right, or some kind of learning algorithm. What I'm asking is that, are there any commercially available software that people use, or sort of the industry standard or something like that? So Weibo must have used some algorithm to figure out. Yeah, I don't know how to compare it to that. I mean, so I guess you need to establish ground truth using that algorithm. Then it doesn't make sense to compare it to that algorithm afterwards. So I was just curious. It was mostly a comment, or it's less of a technical question than sort of I'm sort of trying to figure out this some sort of a challenge here, how to compare yourself to the best algorithm that's known. Because if you use the best algorithm to figure out the ground truth, then I'm not sure.
So then like so you need some, I feel like the most accurate ones would of course be some human labels, but that could be very expensive to obtain.
That's true, but if there are such human labeled data, then I guess that could be a really good baseline to compare it to, and then you can compare your algorithm to the sort of the state of the art other algorithms. So I was primarily curious because Tawhid mentioned some algorithm, and I didn't see that in your list. Some bot, something he said he compared his to. So I was curious as to how people do the comparison. But anyway, more of a comment than a question. Thanks.
Yeah, sure. Yeah, I think like there are many commercial fact checking websites which do the fact checking using human, and they have been running for a while. So I think they may have accumulated some data sets. So it might be worth checking out whether they have such data sets available or not.
Okay, thanks.
Okay. So with this, I'm going to conclude. So in our work, we modeled the spread of misinformation using a Markov chain that focuses on user profiles. And of course, like we could imagine that you can combine such a model with a model that also looks at the message itself, that also reads into the content of the message. Okay, so here our model just focuses on the users. And then based on this model, we formulate this detection problem with the optimal stopping problem, and derived the time-independent optimal stopping rule. And then we developed our algorithm, which is scalable. It's very light for the online part, and it detects misinformation quickly and accurately, since we are minimizing the total cost that comes from the detection time and the accuracy. Okay, so yeah, any more questions? I guess we had a lot of good discussions in the middle.
Yeah, so I think we open up for discussion, questions. Anyone has question, please feel free to unmute yourself. Okay, it looks like we already had lots of discussion in between. So
somebody has a comment on in the
chat.
Oh, okay. Yeah, so Weena, do you want to?
Or maybe Hong Hao can say.
Hong Hao is helping me here. Hong Hao is the one who is doing all the experiments.
Okay.
Yeah, he says the ground truth comes from human checking.
Okay.
So the platform hires some people to report if the news is a fake news or not.
Okay, that's good. Okay, that was part of my questions. Okay, good.
Okay. Yeah, thank you, Hong Hao.
Any questions? If not, thanks a lot, Wena, for this really exciting talk. And also, I think this is the last talk of the workshop. So I would like to thank all the speakers, and we won't have this fabulous workshop without your contributions. So thanks everyone. Also, I would like to thank audience for your participation and very nice questions in between. And if you have any feedback, comments about the workshop, you can let Darat and I know, and also please feel free to let Srikant and Shankar know as well about workshops. They have other exciting workshops after this. Okay.
So actually, there is one more question. It looks like, so maybe you can answer that.
Sure. Yeah. Okay. I can do the remainder of the thanks later. Please go ahead.
Let me read the question.
Okay,
so instead of using Tauhid's algorithm as a means to validate yours, can you use ground truth as an initial condition to update the accuracy of your algorithm recursively, starting from that one?
So I guess the question is about use that algorithm for classifying users, right? That algorithm is not to classify the news, it's about classifying users. So I guess question is, if you use that algorithm to replace maybe your first step with the offline part of classification of users, will that help?
So I'm thinking of like I'm thinking of this is an algorithm. If we have some algorithm for classifying the message itself, then like, because in our algorithm we actually have a prior which we like the initial guess on whether this message is true or not, is misinformation or not. We don't have a very good initial guess. But if we can get that prior information from some other algorithms, I believe it should work better. Like at least empirically, I think it should work better.
Great. So Lei, do you want to wrap up or?
Yeah. So I guess I already thank all the speakers and the audience. I also would like to thank Darat. It has been a wonderful experience of co-organizing this with Darat. And same as him, I also signed up for lifetime for co-organizing any event. Just let me know.
Lei, thank you for your vote of confidence.
Yeah. And I would like to thank Srikant and Shankar again for inviting us, give us this opportunity. And with that, I'll pass that to Srikant for the final closing remark.
Well, first of all, thank you to all the speakers. It was a wonderful workshop, 4 days of great talks. I really learned a lot. And a special thanks to Devavrat and Lei. So here's a request. How about unmuting yourself and give a round of applause to Devavrat and Lei for putting this together. So let's unmute ourselves first. Everybody unmute yourself. Okay, so let's thank Devavrat and Lei and the speakers for a great workshop.
Thank you.
Thank you very much, and thank you all for attending. Bye.